Hey, Bill here, and I'm pretty excited about this first set of videos. My goal is to describe how computers work, and to do it at a level of detail that you could conceivably, with enough transistors, resistors, a handful of discrete components, miles of wire, and a whole lot of time and patience, build a computer completely from scratch. Now, I happen to think computers are pretty cool. I think it's pretty remarkable that we've managed to create these little circuits that can do all sorts of complex operations rapidly. The modern computer, though, is the latest in a long line of devices we have created going back centuries to help us calculate things, from the earliest geared mechanisms such as the Antikythera mechanism, which reportedly found the position of the planets, to mechanical calculators, to the earliest vacuum tube computers. We have found clever ways to perform complex mathematical operations automatically. Now, today's modern computers are based on the transistor, and this first video will start by introducing transistors, how they work, and how they can be used to make switches, and how they can be used to make simple logic devices. There are many different kinds of computers, from embedded processors to workstations, with different clock speeds, the amount of memory they can use, but all computers work on the same principles, as a collection of circuits coordinated by a list of instructions, synchronized by a clock. And the computer we will design will be a simple 8-bit computer. Many of the design decisions we will make along the way will be done for the sake of simplicity. There are things we could do to make our system use fewer transistors or to make it easier to build, but which would make the system conceptually more complex. Our computer, however, will be fully functional, capable of processing assembly language instructions, doing basic math, and making basic decisions. Let's get started, shall we?
Invented in 1947, the transistor is a fundamental building block of most modern electronic devices, including digital computers. A transistor has three connections: a base, a collector, and an emitter. What a transistor does is that when you apply voltage to its base, the transistor allows more current to flow between the collector and the emitter. A transistor lowers its resistance as voltage is increased at its base. This property of a transistor allows us to do all sorts of interesting things, but it's probably best to illustrate this with a sample circuit. Before we go there, however, let's talk a little bit about what we mean by resistance. For those who don't read circuit diagram, these are our resistors. This is our input power. Think of it as the positive terminal on a battery. And this is ground. Think of it as the negative terminal on a battery. Resistance resists the flow of current in a circuit. Think of electricity like the flow of water. Voltage is pressure, current is the volume of water, and resistance is how small the pipes are. If the resistor at the bottom is infinite, that is, it doesn't allow any current to flow past it, the pressure, the voltage, at V out is the same as the voltage at the top. That's because the current has no place to go. And intuitively, this makes sense if you think of electricity like water. The pressure behind the water faucet is there when the water faucet is turned off. But if we start lowering the resistance, the current starts to flow through that resistor to ground. We've opened the tap and the pressure behind the tap lowers accordingly. When the resistance reaches zero, the voltage at V out reaches zero. All the current drains to the ground. The voltage at V out is governed by Ohm's law. See the show notes for more information. The important part to remember, though, is that as resistance lowers, the voltage at V out lowers. Resistance increases, the voltage at V out increases. Now, transistors lower their resistance as voltage is applied to its base. So if we substitute our transistor for our variable resistor, we should see similar behavior. As the transistor's resistance lowers when voltage is applied to the base, more current rushes to ground, lowering the voltage at V out. So let's try this. For a little while, the output voltage remains all the way up. This is because our transistor requires a minimum amount of voltage to start working. This is called the cutoff region of the transistor. It means we haven't quite added enough voltage to turn on our transistor. But now look at what happens when we go past that cutoff voltage. notice that the output voltage suddenly starts decreasing as the transistor allows more current to pass through, and it decreases much faster than the input voltage. For this active range of our transistor, and note that the active range depends on a lot of things, like the type of transistor or the value of our resistors, our transistor has become an amplifier. Small swings in the input voltage translates to larger swings in the output voltage. This property of transistors is why they're used in amplifiers in things like your car stereo or in your phone. But what happens when we turn the input voltage all the way up? Well, once we reach the maximum input voltage, the output voltage can't go below zero, right? The transistor has become what is called saturated. Our transistor is now acting like a switch. Turn on the transistor, the current drains to ground, and our output is turned off. Turn off the transistor, and our output current has nowhere else to go except through the output. The output turns on. Now we can replace our circuit with an input switch and an LED to indicate the state of the output. This allows us to use the transistor as a switch, with the input voltage at the base turning on or off our transistor, which then turns on or off our LED. There is something else interesting about this circuit. As the input is turned on, the output is turned off. As the input is turned off, the output is turned on. Let's tally this up in a table. We'll use the convention that 0 means the input or output is off, and 1 means the input or output is on. This, by the way, is where we get this notion that computers only know zeros or ones. By convention, 0 means off or 0 volts, and 1 means on or maximum voltage. This is our first logic gate, our NOT circuit. The output is on only if the input is not on, and vice versa. Now you may say, well, that's cool, but so what? The thing is, if we're clever, we can do some pretty cool things when we string a bunch of transistors together. For example, if we string 2 transistors in series, we can create a new circuit that turns on the LED unless both switches are on. As we try pressing our buttons in all possible combinations, notice our LED stays on until both transistors are switched on. That's because when both transistors are turned on, the current can finally flow to ground, allowing the output voltage to drop to 0. This is called a NAND circuit, short for not and, because the LED stays on unless both switch A and switch B are pressed. Let's tally up our behavior in a table. As before, we'll use 0 to represent when the input or output is off, and 1 to represent when the input or output is on. As we iterate through all possible combinations, we can see how our NAND circuit works. The output is on unless both inputs are on. Now consider what happens when we put our transistors in parallel. Notice what happens when we iterate through all the possible combinations. The output is on, or 1, unless either transistor is turned on. When that happens, the current drains through the transistor to ground, and the output turns off. This circuit is called a NOR circuit, short for not or. That's because our circuit is on unless either input A or input B are turned on. Now you would think, since transistors operate like a switch, we could simply flip the resistors and transistors and get a functional AND circuit. And this sort of works. Wire this up in a circuit, and you can get a system which turns on an LED when both inputs to both transistors are on. But for complicated systems of multiple gates, this does not work. Here's why. I made the mistake in a previous version of this video of thinking that when you apply voltage to a circuit like this, that applying voltage to the base would cause the transistor to act as an amplifier. But that's not the case. Instead, below the cutoff region of the transistor, the output voltage does not change, and that makes sense. But go beyond the cutoff voltage, and the output voltage rises roughly at the same rate as the voltage at the base. In essence, what's happening is that the voltage applied to the base drains out the emitter. But when we block the emitter with a resistor, the current at the base cannot flow. which reduces the ability of the transistor to act as an amplifier. So when we build a circuit like this, the problem is that the output voltage is not fully on. Chain enough circuits together, and eventually there is not enough voltage to trigger the next gate down the line. This is where the amplification properties of a transistor come into play, because if the on or 1 is not fully on, the next gate down the line will amplify the results rather than dropping the voltage to the point where the circuit fails. So what are we to do? Well, we can go back to the circuits we know work because the transistors are inserted between the resistor and ground. We can start with our NAND gate. Remember, that's short for not and. And we can follow it with a NOT circuit, which inverts the results. This will give us a working AND circuit that plays well with other circuits. Note that the output is on if switch A and switch B are on. This, then, is our final AND gate. This is the AND gate that we will use in future circuits. We can do the same thing for OR. First, we start with a NOR or not OR circuit. Then we append a NOT circuit. This gives us a functional OR circuit which can play well with other circuits. Note the output is on if switch A or switch B is on. This, then, is our final OR gate, the OR gate that we will use in future circuits. Now all these transistors and resistors and stuff can get very confusing, so let's borrow a term from another area of computer science, encapsulation. Encapsulation is just a fancy term for taking something complicated, wrapping it in a box, and using that box as a stand-in for more complicated stuff. For our AND circuit, we use a D-shaped symbol to represent it. Notice we don't draw the power or ground lines, they're implied. For our OR circuit, we use this D-shaped symbol with a curvy back to represent it. Like our AND circuit, we don't draw the power or ground. And for our NOT circuit, we use this triangle with a circle. Whenever you see this little circle on any logic gate, it generally means the input or output is inverted. For our NOT circuit, only the output is inverted. We can see that little circle on our NAND and NOR diagrams. They're basically the same as the AND and OR diagrams, but with the little circle indicating the output is inverted. This idea of encapsulation is extremely important in computer science. It's really the only way you can keep your sanity when talking about something as complicated as a computer. It's how scientists, software developers, and engineers can keep track of the millions and millions of transistors that make up a modern computer. Because we don't. We encapsulate the complicated stuff in black boxes instead. It's not that what's inside is not important, but trying to wrap your head around the hundreds of transistors that make up a circuit that adds integers will definitely give you a headache. But if you can break down that adder into individual pieces, first considering the components of that adder, and consider the parts that make up each of those components, we can keep our sanity, and we can stop worrying about the hundreds of parts when we can think about it as just one component instead. In this video, we described how transistors work. We showed how we can use these transistors to make simple logic gates by connecting them in series or in parallel, or by adding a simple NOT gate at the end. And we described the process of encapsulation, the process of taking complex ideas and wrapping them in a box in order to keep things simple for ourselves. Next time, we will describe how we can use these gates to do basic mathematical operations. We will then describe how we can use these same gates to store intermediate results in memory. And in future videos, we'll describe how to put all these pieces together to execute a list of instructions called a computer program. Thank you for watching.